Welcome you in the lecture series of quantum computing. This is another lecture on Introduction to Quantum Mechanics. In this, we will discuss about review on Hilbert space, inner product of vector space, dimension and basis of vector space. Here you will learn about the significance of inner product. As you know, in three-dimension system, there are x direction, y direction, and z direction. Suppose they are unit vector I in direction of x, j in the direction of y, and z in the direction of k. These are the unit vectors. So any vector A in three dimension, this vector A, it can be represented as ax unit vector I plus ay unit vector j plus az unit vector k. So this is linear combination with the unit vectors in direction of x, y, and z axis. And here ax, ay, and az are the projection of vector A in the direction of x, y, and z axis respectively. So here the unit vectors I, j, and k are the basis. Now you know the property of these unit vector or basis state. It is I dot I, it is equal to 1, j dot j is equal to 1, k dot k is equal to 1. So this is, this is known as the dot product or inner product, and this is equal to 1, and this condition is known as normalized condition. Now if I will take two unit vectors I and j, and if I will take the dot product of these I dot j or j dot k or k dot I, it will be equal to 0, and this condition is known as the orthogonal condition. So here the unit vectors I, j, k, or the three bases I, j, k satisfies the orthonormal condition. Now in correspondence to three-dimensional space, this is the Hilbert space, and it is spanned by three bases phi 1, phi 2, and phi 3. Likewise, in the three-dimension system, a vector is represented by unit vectors I, j, and k. So here similarly, these are the quantum bases phi 1, phi 2, phi 3. Now in this Hilbert space, the quantum system or any vector psi, or you can say the qubit, can be represented as psi is equal to C1 ket phi 1 plus C2 ket phi 2 plus C3 ket phi 3. Here these are phi 1, phi 2, phi 3 are the quantum basis, and C1, C2, C3, these are the probability amplitudes. And similar to three-dimension system, I, J, K satisfy the orthonormal condition. So here the quantum basis phi 1, phi 2, phi 3, they must satisfy the orthonormal condition. And if they satisfy the orthonormal condition, then the integration ket conjugate phi 1 and ket phi 1 d tau, it will be equal to delta ij, and this value will be equal to 1 or 0, and this value will be 1 if I is equal to j, and if I not equal to j, this value will be equal to 0. And this integration is known as the inner product. So if the quantum basis satisfy the orthonormal condition, then the inner product is defined as in the terms of Ket-Bra notation. So this is phi I, phi j, the inner product, it will be equal to 1 or 0. Now let us take one example. If psi quantum system psi is represented as linear combination of two bases phi 1 and phi 2, as psi is equal to ket phi 1 plus 2i ket phi 2. Is this normalized state? And if not, then find the normalization constant with which we can say that this quantum system psi is normalized. So if psi is normalized, then we can say the inner product of psi, it will be equal to 1. Or you can say ket conjugate psi and ket psi integration d tau, it should be equal to 1 if this is normalized. So here we see this is equal to psi conjugate. It will be conjugate phi plus 2i conjugate phi 2, and this psi will be phi 1 plus 2i phi 2 d tau, and this will be equal to integration inner product of these two phi 1 conjugate and phi 1 d tau plus 2I mod square phi 2 conjugate and phi 2 d tau. And you know this inner product is equal to 1 because the quantum bases are normalized. So here we can say this will be equal to 1 plus 2I mod square, or this will be 1 plus 4, it is equal to 5. And you can see this inner product is not equal to 1, so we can say that it is not normalized. So here if if the quantum system psi is represented as a phi 1 plus b phi 2, then we can find out the normalization constant as n is equal to 1 by under root mod a square plus mod b square. So in our question, a is 1 and b is 2. So here the normalization constant, it will be 1 by 1 square plus 2 square. So this is 1 by under root 5. So the new state psi, it will be phi 1 plus 2I phi 2 divided by under root 5. So here 1 by under root 5 is the normalization constant, and the previous quantum state is phi 1 2I phi 2. This is normalization constant, and this one is normalized state. This is new normalized state, and this is previously state quantum state. This was not normalized. So now what do you mean by inner product? It is a scalar product of two quantum states that gives a probability amplitude, that is a number which belongs to complex number. Then the inner product of two quantum state will give you the probability amplitude. Suppose we have two quantum states of light, or two bases, psi I and psi f. This is psi I is the initial state and psi f is the final state. Once we do a measurement on psi I, it transforms to another state, like in coin tossing case. If we measure a state psi in coin tossing, suppose the qubit psi in coin tossing is defined as alpha cat 0 plus beta cat 1. So if I will do a measurement on this psi, it will transform into any one state, quantum state 0 or quantum state 1, with probability alpha and beta. So now the question is, what is the probability of finding particle to come in the state psi f if I make a measurement on the state psi I? The answer is inner product. The inner product is telling you the probability amplitude of finding the system in the final state psi f once you make a measurement on the initial state psi I. So inner product of these two quantum state, it will gives you probability amplitude, and here we operate the measurement on initial state psi I, and we will get the final state psi f. So you know the mod square of the probability amplitude is the probability. So if I will take the mod square of this inner product, it will gives you the probability of finding the quantum state in psi f if I make a measurement on the initial quantum state psi I. Let us understand this with one example. There is qubit or quantum system psi I. It is alpha cat 0 plus beta cat 1. Find the inner product of 1 and psi I, 0 and psi I. So the meaning here of inner product 1 psi I, this is the probability amplitude of finding system in state 1 after making measurement on the quantum state psi I. This is the final state. So here this will be bra 1 and psi I, it is alpha cat 0 plus beta cat 1, and it will be equal to alpha and inner product of 1 and 0 plus beta inner product of 1 and 1. You know the inner product of two same quantum bases, it will be equal to 1 because of normalized condition, and this will be equal to 0. So the probability of a finding system in state 1, it is beta. So the probability of finding the system in state 1 after measurement on psi I, it will be mod square of the probability amplitude, or you can say mod square of the inner product. And you can see similarly here the probability of getting system in state 1, it is beta square. Similarly, this means this inner product 0 phi I, the meaning is probability amplitude of finding system in state 0 after making measurement on quantum system psi I. So it will be bra 0 alpha cat 0 plus beta cat 1. So it will be alpha inner product of 0 0 plus beta inner product of 0 1, and this one is equal to 1 and this is equal to 0 because of orthonormalized condition of quantum basis, and it will be equal to alpha. So probability of finding system in state 0 after making measurement, it will be the mod square of the probability amplitude, or you can say mod square of the inner product 0 and psi I. Let us take another example, psi 1, psi 2. The quantum state psi 1 is represented in column vector with elements 1, 2, 3i, and quantum system psi 2 is represented in column vector with elements 1, 1, 2. And here we have to find the inner product of psi 1, psi 2 and psi 2, psi 1. So the inner product of psi 1, psi 2, it is represented as the bra and cat notation. And if the quantum state is represented as alpha cat 0 plus beta cat 1, then it can be represented in column vector with elements alpha beta. And if I want to represent this state in bra notation, so bra psi, it will be the transpose of complex conjugate. So here the inner product psi 1, psi 2, it can be written as 1, 2 and minus 3i, and psi 2 is 1, 1, 2. Now if do the calculation, 1 into 1 plus 2 and minus 6i, it is 3 minus 6i. Now similarly, if I want to find out the inner product of psi 2, psi 1, it will be 1, 1, 2 row vector into column vector, and it will be 1 plus 2 plus 6i. So it is 3 plus 6i. So here you can see the inner product psi 1, psi 2 and psi 2, psi 1. Both are complex conjugate. So in the inner product, if I am moving this quantum state here and this quantum state here, so it will give you the answer that will be the conjugate of the first answer. Now let us take another example for better understanding. Assume the quantum system cat V is a subspace R square with the basis 3, 2 and 4 minus 6. These bases are represented in the form of column vector. So if I represent this basis, suppose V1, so this basis V1 is represented as 3 cat 0 plus 2 cat 1, and this another quantum basis V2, it is represented as 4 cat 0 minus 6 cat 1. So here you have to find the orthogonal basis of V. So first we have to check whether these bases are orthogonal or not. So to check the orthogonality, if the two bases are orthogonal, then their inner product will be 0. So here the inner product of V1, V2, it should be 0 if they are orthogonal. Let us check. Bra V1, so it will be 3, 2 row vector and 4 minus 6 column vector. So it is 12 minus 12, 0. So we can say that the inner product is 0. They are orthogonal. So set V1 and V2, these are orthogonal. Basis for quantum system V. Cat V. So now let us check the normalized condition. If the quantum bases are normalized, then the inner product of quantum basis with the same basis, it will be equal to 1, just like I dot I1. So if this is normalized, then the inner product of V1, it should be equal to 1. Let us check. V1, 3, 2 and 3, 2. So here it is 9, it is 13. So it is not normalized here. So we have to normalize this, and to normalize, suppose first quantum basis, this is here V1, it is 3 cat 0 plus 2 cat 1. So the normalization constant for this, it will be N1 is equal to 1 by under root 3 square plus 2 square. This is 1 by under root 13. And for V2, it is 4 cat 0 minus 6 cat 1. So here the normalization constant, it will be 1 by under root 4 square plus 6 square. This is 1 by 2 under root 13. So the basis we have, these are the basis. Now the orthonormal basis will be included with the normalization constant. So the orthonormal basis will be here 1 by under root 3, 3, 2, and 1 by under root 3, 2 minus 3. Now addition of two vectors or addition of two quantum systems. So if you have the two quantum system psi 1 and psi 2, the quantum system psi 1 is the sum of probability amplitude weighted with the quantum basis phi 1, and quantum system psi 2 is represented as the sum of the probability amplitude b weighted with the quantum basis psi I. And here in both quantum systems the quantum bases are same and probability amplitudes are different. Now the sum of these two quantum systems is cat psi 1 plus cat psi 2. It will be equal to the sum of the joint probability amplitude weighted with the same quantum basis phi I. So that is the final quantum system has the same quantum basis with the probability amplitude, that is sum of the probability amplitude of the both quantum systems. You know the inner product or scalar product of two vectors cat x and cat y, or two quantum system quantum basis x and y, is denoted as xy in bracket notation. The inner product has the following properties. The inner product of xy, as I told you, if I interchange these position, it will gives you the complex conjugate. So the inner product of xy and yx, these are in complex conjugate form. And the inner product of x with itself x, it will be greater than equal to 0, where the equality holds if x is equal to 0. And the inner product of ax and y, a is the scalar quantity here, it will be equal to the product of scalar quantity and inner product of x and y. Linearity is also hold here. Here the inner product of x plus y and z, it will be distributed here, the inner product of xz plus inner product of yz. Similarly, the inner product of x and y plus z, it will be the inner product of xy plus inner product of xz. And likewise here, the inner product of x plus y and x plus y, it will be the inner product of xx, inner product of xy plus inner product of yx plus inner product of yy. These are some properties of inner product. Previously, we have seen that the inner product is represented in bracket notation, and it will be equal to 1 if I and j are equal, and it will be equal to 0 if I and j are not equal. So this inner product phi I and phi j, it will be equal to delta ij, that will be 1 or 0, and this function is known as Kronecker delta function. And here we have seen that if there is a quantum system cat Va, and it is represented in column vector as the elements a1, a2 to an, and another quantum system Vb, it is with the elements b1, b2 and bn. So if I want to take the inner product of these two quantum systems, then the inner product Va, Vb, it will be in the notation of bracket, and it will be, you know, bra notation is basically complex transpose. So it is a1 conjugate, a2 conjugate to an conjugate. This is row vector and this is column vector. And this inner product, you know, it will gives you the scalar result. And this scalar quantity, you know, it is basically the probability amplitude, as we have seen in the previous slides. So finally, let us take another example. If the quantum system cat x is represented with the column vector with elements 2i, 3 plus 3i and minus i, and you have to compute the inner product of S. So you know the inner product of S, it will be equal to the bra notation. Bra notation means complex conjugate of transpose of S. It is minus 2i, 3 minus 3i and I. This is row vector, and S column vector 2I, 3 plus 3j and minus I. So it will be minus 4I square plus 9 minus 9I square minus I square. So it will be 4 plus 9 plus 9 plus 1, and it is 23. So here you have seen the inner product will give you the scalar quantity. This is probability amplitude. This is the end of this lecture. In this lecture, we have discussed inner product. In the next lecture, we will discuss about outer product and Hermitian matrix. Till then, thank you.